So there's one last type of integration that we've not really talked about. It is possible that it will be on the AP test. The first two examples are going to be pretty straightforward. The second example, you've seen it before, I just want to remind you about it. The third and the fourth example that you'll see are totally different, and you have to use either synthetic division or long division that you learned in pre-calculus to solve those. So I'll show you what that means. So this problem here, you would start off by trying to figure out if there's any other way to solve it. You can't use integration by parts. It doesn't factor. The bottom looks like it could be arctan, but the top is not just a number. So U substitution, it wouldn't work because if you did the derivative of the bottom, you'd get 2x, but you got the extra 4 on top. All around it just doesn't work. So on a problem like this, when none of the other things work and it's a quotient, the first thing I would do is I would separate it. And you can only do this if you have more than one term on the top. If it's just one term on the top, there's no reason to separate it. But you're going to separate it into the integral of x over 1 plus x squared plus the integral of 4 over 1 plus x squared. Now, separately, these two problems can be solved. And so what you have to do is you have to solve them separately, and then whatever you get for the two answers, you just add them. So I will tell you this one is an arctan kind of problem because it's a 1 plus x squared on the bottom and because the top is a number. This one is a U substitution problem because when the bottom becomes the U, you have that x on the top which takes care of it. So what I'm going to do is I'm going to do them separately. So I'm going to do the first one first, and I'm going to let U be 1 plus x squared. Du comes out to be 2x, so you do a 2 in, a half out, and we get the half integral 1 over u, which is a half natural log of u, which is 1 plus x squared. I'll worry about our c in just a minute. I'm going to solve the next one now. Since it's already the form 1 plus something squared, I already know that that answer is just going to be an arctan problem. And it's just going to be arctan since all the 1's already there. The 4 on top just comes out in front. So it's 4 arctan of x, since x is the thing that's squared. And then you put your plus c. So all of this is our answer. Basically, we just separated it and did one of them and then the other one. Another thing that you need to know, the top of this one was a less degree than the bottom. If the top happens to be a bigger degree, like you'll see on number 3 and number 4, this won't work. Okay? So it works when the top is a less degree and when none of the other methods that we can think about works. Alright, number 2. You've seen problems like number 2 before, but a lot of times on these quotient division problems, this one is included. So I just want to remind you of it. You can divide each one of these by x squared. Again, this only works when you have more than one thing on the top. If I simplify that, I get this. I'm going to bring that x to 2 up from the bottom just to be easier to find the antiderivative. And then my final answer is just the antiderivative of this, which is x to the 4th over 4 minus 3x minus 7x to the negative 1. Now these last two problems are the two really different ones. And it happens when the top has a greater degree than the bottom. The very first thing that you're going to do when that happens is you're going to divide. Now, when you have just x plus something or x minus something on the bottom, you can use synthetic division. With synthetic division, I don't know how other teachers have taught you to do that, but what you do is you make this little box. That's how I do it. And the thing on the bottom, the opposite sign, you put it in there. So I put a 2 because I change it from a -2. And then you put the coefficients of what's on the top beside of that. So there's an x to the third, so I put a 1. There's no x squared, so I put a 0. There's no x, so I put a 0. And then there's a number, so I put a -5. You bring down the first number, and then you multiply, and then add. So in this case, I'm going to multiply the 2 times the 1 and put it here. And then you add. When the 0 and the 2, you add. So again, we're going to multiply the 2 times the 2 and put it there. And then you add. So now I'm going to multiply the 4 and the 2 and put it there. And then you add. So what that tells me when I divide synthetically, this last number is the remainder. Let's write that in a different color. The 4 is just the number, the 2 has an x with it, and the 1 has an x squared. It will always be 1 degree less than whatever's on top. So if I rewrite this whole problem, I get x squared plus 2x plus 4 with a remainder of 3. When there's a remainder of 3, that means that we have 3 over x minus 2, since x minus 2 is what we divided by. So by using synthetic division, I've rewritten the problem. And by rewriting the problem, I can find the antiderivative of each piece. It's now to something I know how to solve. So the antiderivative of x squared is x to the third over 3. Antiderivative of 2x is x squared. Antiderivative of 4 is 4x. And antiderivative of 3 over x minus 2 is 3 natural log of x minus 2. Do be careful if that derivative of x minus 2 was not 1. There is something else you would have to do there. But in this case, here's the answer. So you divide to make the problem easier, and then you just find the antiderivative of each piece. There are times that you can't use synthetic division. And it's possible that you can rearrange some things to make synthetic division always work. But I just wanted to show you if it's not like the last one, normally the easiest way to do it is with long division. Notice on this last one how it was just x minus 2 on the bottom. If it was x and plus or minus any number, synthetic division will always work. But when it's x squared, or if there's a number in front of the x or something like that, you're going to have to use long division. So I'm going to remind you how you use long division. X squared minus 2 goes on the outside, and x cubed plus 2x goes on the inside. Very first thing you do is you figure out what I need to multiply x squared by to get x to the third. Well, it's missing an x, so I'm going to put an x up here as the thing to multiply by. When you multiply, you do x times x squared and x times 2, and you write it underneath them. So x times x squared is x to the third. X times negative 2x is negative 2x. Alright. And then you subtract. Because it's division, you subtract. So this is a minus. That's already a minus, so that's a plus. Alright, we get 0x to the third. And then we get 4x. Because 4x is a less degree than what we're dividing by. 4x is our remainder. So if I rewrite this problem, I get x, which is what's on the top, plus 4x over whatever I divided by. And now I find the antiderivative of each piece. This one's pretty easy. I know that that one's going to be x squared over 2. This one, you have to use substitution to solve that. It's back to problems that you just have to figure out how to solve. In this case, u would be x squared minus 2. du would be 2x. And if you want to think about it the way we've done in the past, you put a 2 in, you take a half out. This 4 can also come out. So this is really 2 integral 1 over u. which we know the antiderivative is 2 natural log of u, or x squared minus 2, plus c. So on these problems, the division, it just takes a while to remember how to do that division. And then secondly, the fact that you have different things that to find the antiderivative of, that may make it difficult.